Move over. All right. Okay. So let's see what's going on with the. So not splat. You guys are hear me okay?
Yes, we can hear you.
Okay, all right. So somehow my audio isn't working. I don't know why. Let me. Okay, let me see. Try it again. Still hear me okay?
Yes, the sound is clear.
I don't know why my audio is disabled somehow. Maybe Zoom controller. Yeah, I am not sure about that. I mean, that problem sometimes would happen that if I have an external connector. Yeah. Oh, you think that's that?
And there's also problems now.
No, that doesn't solve the problem.
Turn the volume down on the.
Oh, yeah, okay. Okay, well, that's sweet. So that controls my computer. That's great. Okay, so we are good to go. I think now it's pretty much everybody. So I want to go over the example with you today, and so that I will spend some time to kind of introduce the data set, and then we'll move into the coding part. Okay, so this is the slides that I used somewhere else. I just kind of bring it here for this purpose. So this is the data set that is really agriculture-centric. So it is generated from university statistics from my research group actually, and the data set was collected over the past 3 years. We started in 2016. To then 2017 and 18, and the data that we have mainly is from 2016 and 2017, and we do have some images in 2018. We haven't been processed yet, and we are still planning to do it 2019. So hopefully we can build off a image sets that is quite inclusive regarding different varieties and the different genotypes in the year and the soil background, all those things. Now, so for those of you who are not in agricultural, so this is about soybean IDC, and we all know soybean, right? I don't need to explain that part, but I probably need to explain a little bit about IDC. So IDC stands for iron deficiency chlorosis. So that is it's an abiotic stress. So plants needs to extract iron from the soil for various purposes. So I'm not, I'm not expert to know all the pathways in the plants about iron, but iron is useful for synthesizing, like, a lot of the enzymes, and chlorophyll is also got some iron in it, right? So it's important basically. Now, if the soil is high in pH, what happens is it's kind of immobilize the iron. Okay, so it's basically it's like a tug of war. The soil is gonna hold most part of it, and then it becomes difficult and challenging for the plants to extract the iron from the soil and incorporate that, uptake it, and incorporate that into itself. So, and that's how the iron chlorosis, deficiency chlorosis is coming from, and it is particularly the problem is particularly bad in, like, the Great Plains area, Nebraska, South Dakota, North Dakota, because the soil is relatively high in pH in those regions. Okay? And that's the reason why it becomes important. And the economic significance of IDC is, if you got a problem in IDC, then it appears as it will slow the growth, and then later on it will produce less yield. So, and then you cause the farmers and producers money. So that's the reason why it becomes important that you wanted to know the problem. And there's not really much you can do management-wise. It's not like nitrogen or the water deficiency, right? So if there's nitrogen deficiency, you apply nitrogen. If there's water deficiency, you apply irrigation water. Here, so if you got an IDC problem and you find it, and then pretty much you can't do much about it. You can potentially add soil amendments to decrease its pH and to mobilize some of the iron, but it's an expensive thing to do. So normally they wouldn't do. And to tackle this problem, you can go from the genetics, right? So there are, some of the varieties are naturally more efficient in extract iron from the soil, and you really wanted to use those genotypes, basically. So that's one of the ways, the practical ways to tackle this problem. And so that's the reason why this research come along, because we are working with the soybean breeders, and what they do is they would evaluate a lot of different genotypes in the field, and they know this is a high pH field, got a low iron concentration in the soil. There will be a problem if you got a susceptible species, or versus the resistant species, and then you can see that through the screening process. Yes. Yes, so that's right. Is that that's such a variety isn't existing yet. So that's what they are trying to do, is to you're trying to screen a lot of, and a part of it is trying to understand the genetic basis of it. But a lot of the variety out there somehow is more, for example, it's more water use efficient or nitrogen use efficient, and a lot of the pathways we really don't understand. But we know that we know the end products, right? But there's many pathways that is integratively gets to that final product, and we're not necessarily clear about each and every of those pathways, if that makes sense. And IDC here is the same thing. Potentially, through the breeding program, you can identify varieties that is better, let's say in Nebraska or in North Dakota, and those varieties may not necessarily be the same, but you're still not clear what's the molecular mechanism of it. Okay, so here is some of the background, and I will skip this. So here is some of the background information again. And conventionally, what you do for the screening, field screening for the plant breeders, they would send out a group of students, right? So they train them well, and they're gonna hand them, a bunch of standard pictures, right? And then they cannot sort of train themselves and get familiar with the situation. They look at the standard picture, say they call it 1 to 5, and here we call it 1 to 9, but it's just the more categories you can go with. So normally 1 is being excellent. There's no sign of IDC. 5 being or 9 being fairly susceptible, like all the way to the point that there is no survival, like they're all dead. Okay, and then so we along the way, since we're engineer, right? So we develop something like this here. So we call this a PhenoCart, and what happens is we got cameras on it, and then we are taking head-down images of the plants, and we store that on the computer. And now we have, so we're really trying to get rid of this way. The problem with this is, you got many students in the field, and you have inter-rater confusion into, and the way the student A rate A plot does necessarily agree with another one, right? So this subjectivity can be somehow addressed if you use computer, if you develop an algorithm, right? And then the other problem with this kind of system is if you happen to do the rating in the field on a sunny day versus on a overshadowed day, and then your results could be different. As opposed to if you use an imaging, you can always use kind of standardized color panel in the field of view so that you can actually standardize. We didn't do it here. We didn't do the standardization process. We just use natural illumination pictures. But potentially, if you wanted to increase the uniformity between days, you can actually launch the system like that, even though it's still challenging because maintain a standard color like a panel in the field is difficult. You got the dust, and you got people, you got bird drops, all those things could potentially happen. So we have to think about all those, and that's the reason why we didn't. We feel like yes, it might be able to improve, but the cost for that is probably even more than what you can see with the improvement. So here is that's the background about the data collection. And we, over the 2 years, this is actually 2017. We got a bunch of 2016, I guess we didn't put it in there. So we got about 1,000 images. So you can see, with this kind of system and with this kind of research settings, getting a large number of images isn't really that expensive. We still need to send people out, but we can easily get like thousands or tens of thousands of images with reasonable investment. Okay, so this is quite different from a lot of other disciplines. For example, MRI images, right? It is just not feasible to get like 1,000 images, right? You probably get 100 and you will be, it's already become very expensive, and you say, I will be satisfied with this, right? So, and this is really a difference between the disciplines, and I wish you could understand that, right? So, some people will say, oh, 100 images, not right, but not realizing that how difficult and how expensive it is to generate even one image, right? So, and then we got 2 locations, and we got North Bend and Fremont, all in Nebraska. So we did write a paper about that, and the paper isn't about the ConvNets. The paper is really about just using rule-based extraction of the color feature, the picture features, right, the image features, and then we throw that into a statistical modeling algorithm. So linear discriminant analysis and a support vector machine was the one that we're looking at before, right? And then now we have the capability. We'll probably do the ConvNets and then compare. And the hope is really the ConvNets is going to outperform, a lot of other more traditional methods, right? So, and here are some examples. I will flip on the lights. So, it's kind of, it is not, it is easy for the human to recognize, right? So 1 through 3 is the more sort of resistant type of soybean to the IPC. You can see, so 2 features that we are we are mainly looking at in our analysis for the feature extraction. One is green pixels, right? So if you look at the transitions, it's green on the top, and then when you go to the high numbers, it becomes yellower and brown, and that's a fluorescence, right? So and that's the inability for the plants to extract iron from the soil and synthesize that into the pigments. And then the second feature that we are looking at is really the size of the plants. So all these images are taken roughly at the same physiological stage. They are all 3-4 leaf, three, four. They call it V3, V4, but soybean has three leaflets per leaf. So that's the reason why you see that a lot of leaves. But they are V3, V4 stage. That's the reason why that you can actually use a size because they are all at roughly the same physiological stage. If you got a smaller size of the plants, then highly likely that it is caused by the IBC, right? And then a lot of other stresses here. So one of the problems with agriculture is a mixture of stresses that could potentially happen, right? So if you are talking about nitrogen stress, or if you are talking about the water stress, and sometimes the signal really isn't. It can be confusing to the human being as well. When you look at the leaf, the overall morphology of a corn plants, and it's very difficult for you to say if this is nitrogen stress or water stress. And let alone to develop something which is more automatic by the computer, right? So you really, those are the more challenging problems. IBC doesn't have that problem for a couple of reasons. One is that it's still early in the vegetative stage. You normally don't have the pesticides, you don't have the water and the nitrogen problem yet. So if you see a stress like that, most likely it's IBC. Okay. All right, and also so one interesting thing about IBC is for a lot of these 4, 5, 6, and 7, they are surviving. So 8 and 9, particularly 9. But a lot of those high numbers, but not necessarily 9, they are going to grow. And once they pass in that stage, this vegetative stage, they they will recover. The color will become normal green, but they are very small, so to speak, and they are not going to produce a lot of pop. So that's that's the reason why at this stage it is most sensitive. Your chance to be able to tell which one is more sensitive or resistant is highest at this stage. Okay, then that's the reason why a lot of people say it really needs to do it at V3, V4 stage. Okay, so any questions up to this point? Really? Okay. All right. So here are some problems that we have. This is a real picture, and we don't do a whole lot of quality control. You can see the illumination, right? So those are from the same field. And sometimes if this problem of illumination become really bad if you got a cloudy day, like a cloud, clouds come and go, right? At one occasion, because you're gonna be in the field for 2 or 3 hours, continuous imaging, and sometimes you got a clouds cover, and sometimes you don't, and that also causes a problem, challenge for imaging system because some of the image got like an auto adjustment of the. It can adjust its iris and it can adjust its response so that you're not saturating. But obviously, this one, you look at this one, it does have some saturation problem, right? Because it gets to the green channel, gets to the maximum response, and then it cannot go beyond it, and then you lose the linearity to on the channel. And then you can see there's a lot of background. So soil is slightly different if you're looking at the different fields, but they want to be the exact same color. And some of them got really bad, very intensive weeds. So normally for the breeding program, a weeds problem isn't that big. So because they are very, very careful, and they send people out there, using hand hoes to remove the weeds. Okay, in the production you will have a problem because you don't normally do weeds like on broad acreage. Okay? And then we got the crop residuals. And if you look at this, well, all of them has, but this one is particularly bad. You got a lot of clone residuals from the previous seasons, right? So, and those are the problems we have to tackle using, if you're using explicit feature extraction. Like when you start to develop rules for your image to extract the features, and again, the feature is just the color of the pixels and then the size of the plants. But those would throw off your particularly weeds. It's gonna throw off your results because they are green, right? So and we do develop, this has nothing to do with convolutional neural network because you don't do this with convolutional neural network. This has, this is a conventional image processing. We do need to kind of go over some of the most sophisticated methods and algorithms trying to remove. When we remove weeds, we can only remove the intra-row weeds, and our ability to do intra-row weeds is very, very limited. Can't do it. Basically, we are able to, if you do the algorithm, you are able to kind of identify where the crop row is. And then you can kind of set the threshold by estimating what's the width of the row in that picture. And then anything outside it, if that's a vegetation, then that's regarded as weeds, right? So, but if the weeds is inside the row, it fails your algorithm. You can't do it. So, these are some of the challenges we have, right? And then, so I won't spend too much time trying to explain, but this is the color feature that I'm talking about. Now this is we converted RGB color mode to HSV, and the HSV is hue saturation value, but the hue part is really carries the color information. And we look at the distribution of the plant pixels and the color information, the hue component. And as you can see, so this is IDC2, IDC5 in the middle, and then IDC8 at the bottom. And if you look at the distribution, you see the whole distribution, the pixel distribution shifts towards the red color, right? So, the 2 is sort of, the main value is here. And then, the 5 is, a little bit over there, and 8 is to this area, and this is one of the histogram of this hue component is one of the features that we're using for the classification algorithm. Okay. All right. So let's see what we have here. There's this is last slides for the conventional methods. That this is the field score, right? So those are the 2 values. Look at this, the validation data set gets. One is 46 plus 2 plus 3, and in those, 46 is classified correctly, 2 is classified as 3, and 3 is classified as 4. And we are looking at the blue cells, which is along the main diagonal, and those are your corrected classes, right? The corrected classes. And then we're also looking at the orange cells, just because conventionally people would do it 1 through 5, but we do it a little bit more rigorous. So we get it 1 through 9, and if you look at it, 3 versus 2 and the 3 versus 4, it's very subtle difference. So we want to relax this a little bit and say, well, maybe we can if we consider all those orange cells, we to calculate what the accuracy look like from there, and we get 83% and 85% of the accuracy. So LDA stands for linear discriminant analysis. I'm sure that you guys all know. And RF is a random forest. So we can use a random forest algorithm here. Okay, so that's the background. All right, so I'm gonna switch to, are there any other questions up to this point? It should be all straightforward. Okay. All right, so that's the data set introduction. And then I'm coming back to MATLAB. All right, so I put all these data sets now. I will try to, for you guys to be able to practice, I will need to find a way to transfer those to you. And it's all here. So resize, arrange data, resize data. Okay, so, okay, so it's in here. So it's D, resize data. Why I do this? So I need that. So this is the data. So the first line here is specify the data, location of the data on your disk, right? Now, one big distinction of implementing CNN and other conventional methods is, before when we do an image analysis, we read in the image first, right? It turns out you can't do it with CNN because the image, the size of the data set is so large, and you're talking about megabytes of the data file that you need to read into the memory to do the modeling. So you don't do it explicitly. You can't kind of read in all your data like together into memory once and then in the hope to do the analysis later on. So essentially, I think what the MATLAB do is keep the file on the disk and read them in as needed. Okay, so that you can see that it's really memory becomes a limiting issue here, right? And our computer got like gigabytes of memory, right? And if you read that in the entire, take up the entire memory, and then you don't need to do anything else. You just do that with your computer, and sometimes it's not even enough. Okay, so the data set is here and it is organized. So if you look at that, so we have 4 folders here, if you will, subfolders, and it's all from 2017. Okay, so FM stands as a location code, so Fremont, and the MB is another location code that's North Bend. Okay, and then within each, we got 2. So there's 2 fields, basically 2 locations, 2 fields in each location. So there's 2 fields, and all those are captured in those 4 folders. And then if you pick one and get in, and want to see what's going on inside. Oh, we also resize it. So I decided to resize it because it the original one is like 2000 by 1015. 1500 or something. It's too big. So I decided to resize it to 512 to 512. So if you view it, and all those are the different images, right? So you can see they are all the same format, but they got, some of them got a very different locking, right? So, you got some of the illumination issue that we said before. Here and there, and then you can see some plots are really weedy, like for this one, right? So, so we are throw all of those in the CNN in the hope the CNN can figure that out, right? So, let's see, we got, if you pick another one, and these are all the same. So you see the shade here? So that's the shade from the phenocard, from the mechanical system. Okay, so that's another thing that you have to worry about a lot of the time is it has nothing to do with size. It's just if you want to hold an instrument close to what you want to take pictures, that instrument have an impact on the object that you wanted to measure, okay? Yeah, so, and you can, and I was trying to find out ways. This is a relatively large data set. So 1,000 images, about like, well, maybe like 50 megabytes or so, okay? But again, I said, there's no way MATLAB can read all of them into the memory first and then starts to analyze it, okay? So that's the reason why didn't happen. So you got so what MATLAB do is it got something called. So remember, so when we look at when I gave you previous examples, we use ImRead. So ImRead really is a function to read in reading the image from the disk. Here it didn't do it, right? So it says the image data store. So image data store is essentially it's a data file format that handles the CNN data sets. So it doesn't appear to read in anything. It's actually kind of peek through everything in there and then trying to develop indices. And then, when it starts to read in, then it read in as batches. Okay, and then when you finish using it, then release it from the memory such that the next batch can be read into. Okay, and then so you got the digital data path again. That's the where it is, and they include the subfolders. That means remember that I got 4 subfolders. The actual image is in those 4 subfolders. So then this is the reason why this thing is there, so that the MATLAB know that when it look at the pictures, gets into those subfolders, get pictures. Okay, and then this is fairly important. So the label. The label is your cat or dog. In my case, it's 1 through 9, right? And then it's all predefined here. It is, so if you look at this, so it's, this got the, all those labels, and if you get to the very end, so that's 1019. So that's the number of images we have, the exact number of images we have. Okay, distributed in those 4 folders. It is very important that you have your label and the sequence of the image have that 1-to-1 correspondence, right? And that is, you will probably need to spend 90% of your time just to do that, because you can imagine, if you're off by 1 or by 2, then you're screwed. You can't do that analysis anymore. So be really careful about, you can put everything in 1 folder. The reason we didn't do that is because I wanted to keep all those location and year information. And I don't want to mix all of them together. Then I lose that information. And then it's very difficult for me to go back if I wanted to say, I just want to look at 2017. If I just want to look at the images from this location, I can still do that, right? So that's the reason why I'm trying to keep everything separate. All right, so that's the important part. So, and this is the label, okay? And then, so this is image data store. It's an object, right? It holds the image indices, seems like. And then once we have the label, and then you also get the label into its label property, basically, right? And then, your image data store got 2, you got 2 properties. One is the image indices, and then the other is the label, and the training is happening through those 2. Okay, and then it also provide a really nice function. It's called count each label. So count each label basically helps you to count labels, right? So you can look at, you see, I will say label count, and it's actually print out a table, and it shows you the distribution of those classes. This becomes important when sometimes you have a really imbalanced, imbalanced classes, right? So if you have more female than male, way more female than male, then you have to kind of use some strategies to balance your algorithm. And this becomes really nice now. So you can see here, so my data set is also imbalanced, right? I got more class 1s, means, insensitive varieties. And then I have 2. Now this is a problem in artifacts. This is a problem just, people, the human reader can't distinguish very much between 1 and 2, right? And then, they are more inclined to assign a 1 than 2. Then, if that is true, then you will have this kind of effect, right? You got more 1s than 2, but the 2 is, way less than many others. Like, 3, 4, 5, 6, and 7, it's sort of balanced between 100 and 150. And we have less 8 and 9, which is normal because 8 and 9 is really kind of, those are not very worth further investigating in this kind of context, right? It's all dying. So, and that's, this is a really nice feature. And then, this also, this line splits the labels, right? So you can do random. Random would guarantee actually each label got it's actually will be a balanced split if everything is true random, right? But this is even more explicit. Is I want a label one, and then if I want to choose 3/4 of label one gets into the training set, and the remaining goes to the validation set, and it's gonna do all of do the same for all of the other labels. So that's the split each label function mean, right? Now you don't have to do that. You can do random. So if it's random, then it should be roughly proportional, okay, for each of those labels. Yeah, so along that line, so what are the other sampling? So this is actually pretty important. So for the sampling scheme, how many sampling schemes are there? So we get a random sampling, and we all know, right? What are some other sampling schemes that is widely used in your research? Random is the only one you guys use? Okay. So in our discipline, we use a lot of what we call a stratified sampling. So basically, you group your population by some property, and then draw random samples from each of those groups. So it's strata. We call a strata. So the stratified sampling. Okay, and you can do some of those things here too. All right, so that's we kind of define the data storage object, and then we developed a training and a testing scheme, right? So training is 70%, 75% of the data, which is because we have roughly 1,000 images, so that is going to be 750 images for the training, and then we got 25%, which is the 250 for the validation. Okay, and then this layer information really is what we have here. Okay, so now this is the key for the CNN, and this is so. I didn't really give a whole lot of thoughts at all. I'm just sort of kind of grab the things available. So there's no indication that this layer, a CNN topology is best for this particular problem. There's no indication of it. I basically, pick the 2D convolutional layers. I pick the ReLU activation, and I throw in some maximum pooling, and then I do, I do more 2D convolution, and then I throw in a dropout layer to reduce the overfitting, and then I got two fully connected layers here. So that's essentially, I see those available, I grab it, right? There's a lot of fine tuning with this for a particular problem. Now, if you have a problem and if you wanted to use this method, and you are not going to get it right the first time. Okay, well, you can get indices, you can get a performance, but I think you have to tune in a lot, and a lot of your time is going to spend on this, trying to define this architecture, basically. Okay, and if we look more carefully, now input layer is I resize those images 512 by 512, and those are RGB, and that's the reason why the 3 is there. Okay, and then convolutional 2D, I use a 5x5 filter, and I use 16 of them, and I padded them such that after the convolution, the dimension in the X and Y is the same as the original. And I got the the batch normalization, you got the ReLU. Okay, and then there's another 2D convolution, and I use 3x3, I use 32 of them. Okay, and this time I choose to use a stride of 2. So basically, I do the convolution and I skip one position, and then I go over to the next one, right? So I do that, and that's the same. And the maximum pooling that we all know is a 2x2 grid, and among those 4 elements, I extract one which is the maximum, and I also do a stride of 2. And there's 2 more convolutional layers, right? It's 3x3. I use 46 of them, 64 of them, and the padding, the striding is also there. All right, and then after I got to here, drop out 0.5, then I have, and I roll them to 1D, and then I got that to another fully connected layer, which got a 64 of the neurons. Okay, and then get another value layer, and then the fully connected layer, which is 9, because I got a 0 to, I got a 1 to 9. Okay, and then that connects to softmax, because I'm doing a classification problem, and then I do the classification layer. Okay, so that's basically the neural network structure. And don't ask me why, I just gonna put them together, okay? So there is no, yeah, so this is not optimized at all. All right, and then we are scrolling down and look at the options, right? So the training options is where you throw in a lot of those hyperparameters, so to speak. Okay, we already have some hyperparameters, right? It's specified here. For example, the dropout layer, 50%, that's a hyperparameter, right? It cannot be trained, and you can pick 0.4, you can pick 0.7, you can pick 0.5, okay? And a lot of these, you know, the 5x5, there's a hyperparameter. You decide to use 16 of them hyperparameter, right? You use a lot of hyperparameter already here, but there's more that you need to specify in the option. So SGDM, right? So that's a stochastic gradient descent with momentum. That's one of the training, you know, the gradient descent option that you can have. And we already see the epoch. So epoch is, you know, the how many times you want to train, go over the entire data set. Now remember, our training set got 750 samples, right? So which means, and then I also, you know, specify the mini batch size of 32. So which means, you know, you're reading 32 images and then go over the forward, feedward training, and then backward propagation. And then that's one. And then you're reading another mini batch, right? And then, so because we have about 750, so you almost need to read in this mini batch a couple, 20, 25, you know, between 24 and 25 times. Then you finish one epoch, right? And then you have to do this 10 times. So that's so the you know, how many kind of, you know, the forward, feedward training, and then the backward gradient descent that you have to do. And then we got the initial learning rate, and again, that's a hyperparameter. And normally the guidance is, you know, 0.1, 0.01, 0.001, 0.0001. You just pick one, and that's how, you know, the you know, it would be silly that if you see that I decide to use 0.25. Normally people don't do that. I mean, you can if you wanted to. So, but those, you got some of the, like, recognize the values. And also the mini batch size is the same. You know, people normally use 32, 64 is most common, 128, and this is just a reflection that the computer science wants to like exponential of 2, right? So, you know, you can do 10, 20 if you want. And then, you know, you got the validation data, right? So that's your validation. And then validation frequency is 30, means that, you know, after 30 mini batches, after 30 mini batch training, do a validation to report, basically to report to you what's the accuracy of the validation, okay? And then I'm not sure what's the verbal, so I guess it's a print out. Like, what's the print out? And then plots, you know, we see the plots before, okay? All right, so this is the option, that's the training option, a lot of hyperparameters. And then I'm gonna go down with the training, all right? So I'm not sure if it's gonna be successful because seems like everything is run on my local computer with GPU. Okay, so it's a default is GPU, so I do have a GPU here, no problem. I trained it successfully yesterday. It takes about 15 minutes on my computer to run. So let's see. Hopefully it will run. Sometimes it won't because it says that your GPU is out of GPU memory or something. I hope this won't happen today. All right, so give it some patience because this is slow, okay? And you know, we are not, you know, this is a medium-sized data set. You know, compared to a lot of other applications, this isn't large at all, okay? But this is, again, this is very similar to, that letter size problem, right? The letter problem 0 to 9, and it's very similar to cat and dog problem. It's a classification. We're not doing, all right, so it's actually running, so that's good news. And see, that my memory stick is flashing, means it's reading the image from here, so it's reading in batch wise. All right, so it starts to train. All right. So you can see, so right now, so at the beginning, the accuracy is 10%. Right? That's normal. That's a random guess. So it's it's when you start to initialize your weight, have no idea, and it ought to be random. So it's the overall accuracy is only 10%. And let's see if it's gonna kind of improve that a little bit, or how much improvement that can be after the training. And I do see, yesterday when I see the results, I do see some quite interesting patterns. And and we can look at this later when we finish. So I hope this looks like it's running a little bit faster than yesterday, because yesterday I'm multitasking. I'm also reading PDFs when I do this. Yeah, you see, overall it is improving, right? That's now it gets to around 20, 30%. So that's good news. And then when it gets to, the 30 mini batches, roughly at one epoch, it's gonna run a validation. So that bringing that 250 validation samples, and with the current setup, the weights of the neural network, do a prediction. And it would have also plotted here. So you see it can go down, right? So I don't believe so. It goes down because it missed the optimum point. So when it's when the great descendant missed it, and then somehow it's trying to coming back. It will come back, but yesterday when I see it gets to the accuracy 50%, and it won't improve. And then the structure that I built here, it got a severe problem that you can see. So right now you see the first validation here, which is highlighted in dashed line. So that's roughly 30%. Now it gets to the second epoch. So we said that we're gonna run to 10 epochs, so it's gonna be quite long. I just want to wait until that I see the interesting trend that I saw yesterday, and then we don't have to wait until it's finished. But overall, you can also see the loss, which is at the bottom, and the accuracy. You got an overall trend at least now, right? So it's trying to improve. I think now it's run another validation, and that's the reason why it gets long. So now validation gets to around 40%. So if you I have seen use Python is faster, and even though my own single computer, you are not going to improve that a lot. Right? You are limited by the physical computation that you can have with your machine. Python make it easy to get that to to the HCC or a cloud surface or something. If you got a huge data set, if you got a high resolution images, you get like images that if you got like tens of thousands of images, then probably here isn't a solution. Right, 15 minutes for this, and then I guess it's not the increase of computational time isn't linear. So if you got like 10,000, it probably takes you like a few days. Then you will be really right. So. You see the two blue curves. One is a little bit more fainted than the other. So the brighter one is the one in the background, the fainted one is instantaneous value, and then the more brighter blue one, that's the running average. Okay? It's a little bit more smoother. All right, so it gets to close to 50. All right, but now here is what I want to point out. And as the training going, you will see this problem more obvious. Is it seems like there is a difference between the training accuracy and the validation accuracy, right? So later on, I do believe that the training accuracy can go up to like 70, 80%. But the validation accuracy will remain the same. It was, so we'll see this pattern maybe in like epoch 6 or something. So that's, that gets a problem, right? Your model fits the training data very well, but it can't generalize as good for your validation data set. And potentially, and we can discuss later on, potentially there are ways to improve this. Like you can do augmentation, and or if you physically, if you can afford it, you should go out to collect more images and label them manually and include that into your data set. But you can also do some like augmentation, trying to rotate it and flip it, flip it both ways, and then sometimes you can share it, even though, share it might not be a great idea. I don't know, but you see all those in the literature. Okay, but fitting, it's a very common problem, fitting well in your calibration data set, but it doesn't really generalize very, very well for the pictures that's never seen by the model. So yeah, all right, so almost the 50%, right, of validation. So that is, so compared to our conventional method, so that's about the same. Our conventional method, you remember I got two accuracies, 1 and 2. One is just the strict major diagonal elements, and that's about 50%. So I do believe this won't go up anymore. So 50% is really what we see. So what's the indication? So indication is for this particular problem, convolutional neural network isn't really particularly good compared to the LDA and the and the random forest, right? But my feeling is I would still rather probably go this way, because that doesn't take much of my reasoning to remove all the weeds, right? So that our conventional method doesn't rely heavily on our success to remove the weeds. If weeds are there for a lot of pictures, for significant proportion of the pictures, then our algorithm isn't work very well. So this doesn't really require to do that, and this is more of a lazy man algorithm, right? Which is you develop an architecture, and I don't even kind of give a lot of thoughts how to build that architecture. I just trying to grab something and make it happen. But even that, you see, here is a problem that I'm referring to now, and you can see, and those two curves will separate wider and wider. So training would go up, right? But your validation wouldn't. Okay, so and when you report your results, and you want to be really careful about what accuracy you are. I guess you are through this class, and you know that you shouldn't just report your calibration. A lot of people do that. Are there any questions about this? Yes.
Theoretical point. This isn't like binary classification. It's like, am I right in saying that 50% is still better than Bitcoin?
Right. No, yes, exactly. So 50% in this particular case is actually fairly good. Your random guess flip a coin is 11% because you got nine classes. Right. Yeah.
Which is why we started with that.
Correct. Right. That's the random weights. So you see that the separation of those two curves, right? And that is really well, this is an indication that your neural network isn't for this particular problem. There's a lot to improve. The ideal situation is you would see after some epoch of training, those two curves are not they are very close to each other. Your training might be a little bit higher than your validation, but not like this. Okay? Right, okay, so I think if we make it a point, we don't need to wait until this is done. And after the class, I hope that somehow I will transfer all those images to you, and then this code, and then you can play with it. You can try to change the hyperparameters, or change some of the layers, change the parameters there, or drop one layer, or add one layer to see if you can to run it at least a couple of times, and to see if you can have a better performance, or you can compare with each other. Okay, and for the next class, I want to be here next class because there's a meeting I have to go, so I will cancel that so that you can kind of practice this one. Next Thursday, I will call one of my graduate students. There's the same problem, the same everything is the same, but he's gonna run it through Python. Okay, so he's gonna, if you have a computer, maybe you kind of install the Anaconda, the Python notebook, and then maybe that, it's easy. So Python is really, it doesn't take you much time to install it and get that on. And I can find the instruction and I can kind of get you there. And then in Python is even nicer than this because everything you will be able to see the immediate output like right next to it. Okay, you see now you can see the problem. After some training, then you got your validation actually goes down. So that's the reason why a lot of people say early stop. Like there's a strategy called early stop, and this is exactly why you need to stop here. So that's your best training. With this with this set of parameter and this neural network architecture, you shouldn't train more epochs because after a while it goes down. It seems like it missed that minimum point to go to somewhere else. Okay. And it, see this, this is still keep going. Yeah, it's overfits a lot, right? Okay. All right. So yeah. So that's everything I want to say. And don't forget your class project. Okay. Yeah, and it's almost done. Let's get yeah, it's got a 1E box. Yeah.
Labels are actually off.
Which label?
The epoch labels.
Mm-hmm.
They're supposed to be declared.
Yeah, no, yeah,
Maybe it's
it is, it's, I should say, I got a 750 image. Well, it's not the exact 750.
the text.
Yeah, right, yeah, correct. Yeah. Yeah, so this iteration should be mini batch iterations. And each epoch we said is going to be roughly like 25, 20, not 25, not exact 25, but it seems like they are not off by a lot. How much more left? Okay, 8 iterations, okay, 7. We're almost done there. This runs actually a little bit slower than yesterday. Maybe it's too hot here in this room. Right? Yeah, so you can train long enough to get to 100%, even for this problem. But it's meaningless, right? So don't fool yourself. Yeah, so this is the exact problem that I want to refer to. Okay, so you got a huge gap between your training and the validation, and there's a problem. Okay, so that's done. All right, so and then your final accuracy for validation is roughly 50%, which is better than 4 times better than 5 times better than flip-boy forming in this particular problem. Okay, all right, you're free to go. See ya. Not bad, folks. We're done here. So hope that you learned something today. Don't forget that we will not have class next Tuesday because I'm in a meeting. But we will still have class next Thursday. We'll show how to run it through Python. Okay.